So volcanism is a direct result of the movement of tectonic plates, in all cases except perhaps one. And we'll talk about the exception to the rule. So what I want you to be able to do is to identify various types of volcanic landforms and distinguish between them. What are they composed of? What is their height? What's causing them? What kind are they? So when you look at this volcano, I think all of you would probably, if you were in 3rd or 5th grade, when you talk about volcanoes, most everybody would draw this, classic type of strata volcano with the lava coming out. You might even have made one for science with the baking soda and vinegar. And that is definitely one of the types, but there are so many more that we can think about. And one of the things is to first think about this idea of there are active volcanoes and inactive volcanoes, and we call them active if they have erupted at least once in recorded history. There are about approximately 50 volcanic eruptions a year, and we have had 70. Most of our we have about 70 volcanoes. Most of them are inactive. And they look at that recorded history of where are they hazardous based on in the last 15,000 years. And if you look at this map, you can see, okay, the pattern, relatively, volcanoes are in the western part of the United States. I see no volcanic activity in the east and the south. There's a few in the southwestern states, but by and large, the most active volcanoes are along the Cascade Range in the Sierra Nevadas. We can also look at the ashfall hazard, as we saw when Mount St. Helens went away. So where do earthquakes occur? So I said earlier they occur at as a result of tectonics. So they occur on these subduction boundaries, inland a bit. In Oregon, we have about 55-60 miles inland from the subduction of the Juan de Fuca plate. We have that Cascade volcanic range. These volcanoes happen as a result of seafloor spreading, so at divergent plates. And then we have these odd places called hotspots where we have volcanic activity. And these could be a result of superheated mantle movement, or a place where maybe the crust or the seafloor is a little thinner. So I have this image showing plate boundaries in black here, and the areas where we have earthquakes are along these black lines. So we've got these are subduction earthquakes. So if we look at this link, Volcanoes Index, let's see if I can open that. And I think this is in your notes as well. And this is a really cool map, and I made my screen so small, sadly. If I can find that. No, where did it go? There it is. Okay. So this shows places in the world. So there's a yellow symbol, and I think yellow means increasing advisory. So we've been watching Hawaii, so there's an advisory here. The green along the western is kind of normal, so there's no activity. There's this one with an eye. I like that. So that's a level of concern out here out south of Alaska. And I don't know globally, if there's any others. No, they don't seem to be tracking other places in the world. So this looks like maps you guys could be making. So we have all kinds of volcanic activity, and it's just really interesting that there are so many here, but you can see these edges of the plates. So here is some subduction zones here, and you have volcanic activity. You have subduction zone there and volcanic activity. If we had a world map, here is subductions here with volcanic activity there as well. So when you have a subduction zone, see if this will, oh, so cute. You have that heavy basaltic seafloor subducting underneath the continental plate, and as that layer gets deep enough, it remelts. It's kind of like an amazing recycler, and as it remelts, convection currents happen. It becomes buoyant, lighter, and it bubbles up to the surface, creating this volcanic arch. So in Oregon, we have mountains along the coast that are the result of tectonic uplift from the subduction zone, but we also have these volcanic mountains inland along in Oregon and the whole Pacific Rim, or the Ring of Fire. So while this one is subduction zones, these are divergent areas. And it looks like I have two. Why do I have? Oh yeah, because I had a student that was colorblind for a while and couldn't see red, but I'm not sure that that was helpful. But anyway, so here's a map showing divergent. So these plates are pulling apart, and you have volcanic activity all along these areas where you have plate movement separating. And then this is the location of hotspots, and you can see for the most part hotspots are not always associated with the plate boundary. Now, Hawaii is the hotspot volcanic arc that we're the most familiar with in the U.S. However, Yellowstone is also a hotspot, and that geothermal activity in Yellowstone is a result of some kind of crustal activity or thinning. So what is a volcano? So a volcano is basically some kind of structure in the crust. There is a central pipe or a vent. So think of this as a tube that is a conduit for magma. Remember, magma is the liquid rock under the surface, and lava is the rock on top of the surface. So you've got this vent, this central pipe, an opening for the magma, and the magma can produce many different kinds of things. It can produce a lava flow. It can release gas. It can release pyroclastics, which are explosive rock material blown up into the air. Ash is a type of pyroclastic. So volcanoes can produce different textures, different consistencies of material out their central vent. So when we think about a magma chamber, it is a layer under the surface of liquid material, and it can have small vents with other domes or layers happening. In Oregon, some of these are in Eugene. We've got Skinner's Butte, which was a vent with a magma dome that eroded, and we can see those layers. So we have this, whenever you have these chambers, there can be vents connecting them, and liquid magma moving. Lava expressed on the surface usually comes in two types. Basaltic lava can be which is very high in silica. It's very thick, very sticky, very angular. And then Pahoehoe lava, which is ropey and smooth. So Pahoehoe has very low amount of silica. It's very runny. Pahoehoe would be hotter lava, kind of the difference between Hershey syrup and hot fudge. You know, one is a little gloppier, the other is much thinner. When we look at the type of explosions or development that volcanoes can have, they can be categorized either as explosive or effusive. And an effusive volcano is very common with divergent plates and also with hot spots. So they can have a large amount. You know, when people have effusive speech, they talk a lot. But an effusive volcano, there's lots and lots of lava, huge amounts of lava. It's very, very low viscosity, means it's not very sticky. And the lava just runs and runs and runs for miles and miles. It's like less than 50% silica. And this is very common of the Basin and Range in Oregon, which creates these plateau basalts, or the shield volcanoes in Kilauea. Explosive volcanoes are more commonly seen around subduction zone. They have a tremendous amount of silica, so they're really sticky, they're thick, they're gooey, they plug up the vent, pressure builds up, and then they have these gigundous explosions with pyroclastics and ash and gas and lava and all kinds of drama. And so this is very common with composite volcanoes or strata volcanoes. So I want you to be able to identify the shape, the size, and the type of lava, explosive or effusive, that you would see in a cinder cone, a composite volcano, a shield volcano. I want you to know about flood basalts and what's a caldera. So we'll start with the smallest feature, which is a cinder cone. And these tend to be explosive, although they're pretty small, so their explosions are not devastating. But they're these perfectly shaped little volcanic hills. They're typically less than 1,500 feet high. And so that's one of the clues. If you have a cone-shaped mountain that is only 1,200 feet in relief, so we're talking about from the top of the cone to the base of the cone, that's probably a cinder cone. They don't have a lot of lava flow, but they have lots of little eruptions of ash or pyroclastic. So ash, cinder, small little lava bombs. And Black Butte, Oregon Lava Butte would be examples of these cinder cones. Here's a series of cinder cones along in the Rift Valley. I mentioned lava bombs. So lava bombs are kind of pear-shaped rock formations, and you can think about hot lava being thrown up into the air, and then it gets shaped aerodynamically as it falls. So these are kind of wind-shaped or air-shaped rock objects that are exploded. Scooria is lava that has a lot of holes in it, and basically these holes were gas bubbles. And so when the rock is molten, it's not a solid rock, but there's a lot of gas bubbles, and so the gas bubbles create this kind of wholly open pitted rock. So here is an example of a cinder cone. It has a central vent, beautiful little cone shaped, and if you measured the height, so there's a car right there. So it's not very high. It's got to be under 1,500 feet. So this would be a classic cinder cone. This is a cinder cone in Oregon at Lava Butte, and I think there are some practice maps that you'll be looking at the Lava Butte volcano, but there's cinder cone, and this is a road that goes up and a little bit down into the crater of Lava Butte. This is Lava Butte from the side view, so you can see this scoria this lava on the side, and then this just looks like a gravel pile of red lava. Here's some other, again, you can see this central vent. Sometimes when lava oxidizes, so it will get superheated in the gas and the steam and the moisture, and so that black basalt will actually oxidize itself and turn red in the process of explosion, and that's kind of what happens up here at Lava Butte, and you can see some of that oxidized lava or scoria inside those little cinder cones. The Composite Volcano or the Strata Volcano, again, is the one you would probably have made in kindergarten or in 3rd grade or 5th grade. 60% of all the volcanoes that we study are stratovolcanoes, and if you go back and think about that ring of fire, so these are subduction zones, and the ring of fire is mostly stratovolcanoes. So there's a lot of areas and up here in the Mediterranean also. So lots of stratovolcanoes in the world. Where am I going here? And so they're cone-shaped, like the cinder cones, only they're much, much bigger. They have that depression again. They have that in the summit. I'm going to fix that because I can. So the interesting thing about stratovolcanoes is they're not all scoria. They have different strata or layers that happen at different events. So at some point that volcano may get really sticky and thick and then have an explosion of pyroclastics and ash. And then maybe once the vent is cleared, now lava will flow for a while. And then maybe it'll settle down and you'll get some soil growth. And then maybe it starts to become active again and you get more ash, or you get lava with different kinds of materials so that you might have more andesite, less basalt. Andesite is a type of magma that is much more explosive, and so examples would be Mount St. Helens, of course, Mount Fuji, Mount Hood, and you know, what do Japan and Oregon have in common besides stratovolcanoes? I hope you said they're both on subduction zones. So this would be the different strata. So you've got your pipe materials coming out, and this is an interesting phenomena in that one side of the volcano doesn't have to match the other side of the volcano, but so depending on whether maybe the vent changes or explodes out the side, so they have you know, very different structure, but definitely showing pyroclastics, so explosions with ash, lava flow. And then here is a nice composite volcano in Costa Rica. Example of Mount Fuji. So we've looked at cinder cones, we've looked at stratovolcanoes, and then the third is shield volcanoes. So the other two have explosive lava with high silica content. The shield volcano is effusive. So it doesn't have huge eruptions. It can have a lot of lava. It's very hot, very low silica. It flows for a long way. So think about a can of Hershey's syrup, and you get that can of Hershey's syrup hot and you pour it on the counter. It's just going to run everywhere, right? If you get a can of hot fudge sauce and heat that up, that's going to stay more in a glop, right? So the shield volcano, the effusive lava, is much more like Hershey's syrup. Very hot, flows forever. And so over time, it builds these very low kind of shield-shaped features. They are not the high cones because the structure, the material is too fine, too thin, too runny to build these very steep-sided features. And so Newberry Crater in Oregon is an example of a shield volcano, and in Hawaii, Mauna Loa. So here is a shield volcano, and these are huge, huge features. If we go back and look again at look at the slope here, you've got a much steeper slope compared to this shield volcano. And if you took Mount Rainier, which is a strata volcano, and you put it at the base of Mauna Loa, Mount Rainier is pretty small. But part of that is because most of Mauna Loa is under the ocean, right? And Mauna Loa is just a huge feature.